All right, so I'm honored to introduce our next keynote speaker, Professor Geoffrey Fox. Professor Fox is a distinguished professor at Indiana University, and he's had a long and distinguished career making fundamental contributions to HPC, parallel computing, grid computing. And interestingly, he's not been happy just to focus on the theory, but he's been applying, a lot of this compute infrastructure that he's been building to a broad variety of use cases, including biology, geology, chemical informatics, and particle physics. It's had an impressive history of publications and awards, and I just want to highlight one recent award that he got a couple of months ago, which was an Expeditions in Computing Award from the NSF, and this is for his work as part of the Global Pervasive Computational Epidemiology Project, which is very relevant to our COVID-19 pandemic situation now. So he's part of a team that's trying to understand the complexities of infectious diseases and real-time epidemiology. And today, Professor Fox will present some insights that he's got on kind of the symbiosis between HPC and machine learning. So not just how HPC can enable machine learning, but how ML can enhance HPC. Right, Professor Fox. Can you share your screen? We see your video, but I don't see your screen yet. Okay, I see it now.
You have my screen? All right, can I start?
Yes, go ahead.
All right, so thank you very much for the honor of this invitation. And well, I'll just get started. All right, so we're going to talk about something about the interface of HPC and machine and deep learning. And here's this first slide. So if we look at how machine learning or deep learning interfaces with HPC, it seems relatively obvious that it ought to be important, because if you have big data, you probably want big computing, and almost by definition, HPC will get you better performance. And certainly deep learning has made that relatively clear, as we heard in, for instance, the last talk, and it was implied in the first talk as well. I went to this conference, MLSys, which seems a pretty interesting conference, pretty relevant to this one, actually. And effectively, every single paper there used HPC. They didn't know, very few of them discussed HPC, but they all used it because they were all discussing deep learning and its execution. Another important point is that when you talk about HPC, at least in the US and I think most of Europe, actually the HPC community does a lot of the data analysis. And things like e-science and grid computing came from the HPC community. So that part seems relatively clear, and I think actually relatively well established. And as I'll point out, there seems to be little unclear about how we merge the use of GPUs to do deep learning, which is a relatively clear, well-defined activity, with the broader aspects of data analysis. The other area which I've done most of my recent work on is actually using machine learning and deep learning to help HPC, and I will discuss that. That is what Dean called machine learning for systems in his 2017 talk, and I think that's very important. Another general sort of simple remark is that though we talk about machine learning and AI, today most of that appears to me to be deep learning. And that's also a little confusing, because a lot of the work of 5 years ago was formulated around machine learning, which I think has slightly different characteristics from deep learning. Another sort of interesting feature of high-performance computing is if my students say want to get a job academically, they're much more likely to get it if they focus on machine learning or deep learning than if they focus on HPC, which is not terribly healthy academically, or more generally, even cyber infrastructure is not so healthy. However, in industry or DOE, HPC is pretty healthy, and the reason is HPC is clearly useful as a implementation technology. It's essential. Whether it's healthy as a research area is not quite so clear, in my opinion. All right, here is a little graph which is rather confusing, except that it has only one point. It says that if you look at the compare HPC or parallel computing for data-intensive problems with parallel computing for simulations, they're actually pretty similar. They each have different types of problems, some which are very difficult because there's a lot of irregularity, some which are very intense computing, like the GPU computing in deep learning, some which actually probably dominate in terms of applications, are pleasingly parallel, and all of them are seen both in simulations and data analysis. And so it is really, there's a lot of synergy between HPC for simulations and HPC for machine learning. And now here's a slide which it comes from this paper from I think they're from Google, which points out that if you look at the machine learning part of an application, it's a rather small part. I've made it red here in this graph, which is in this plot of an overall system. But if you look at the papers are all on the red part. Like at MLSys, this conference I went to, I think every paper was on the red part, not on all the parts around it. And I think if you look at the day's discussions, there is not a very clear distinction between what I call data engineering, which is all the stuff outside the red part, at least I'll use that term for that, and what goes on inside the actual deep learning or machine learning kernel. All right, so that's something to bear in mind, that there is not a clear distinction between these 2 points, and not clear idea of what the key issues are. All right, so now let's look at machine learning for HPC. So if you look at using machine learning for high-performance computing, I did some work with Shantan Najjar. I read only 100 references, which were over the last 3 years, which is probably 10% of the total. And there have been lots of recent papers since we published our paper last September. And we divided the way that machine learning was used to help HPC into 3 areas. The first area was using the machine learning to improve the configuration. That's, you might call auto-tuning, or by data integration, that could be called data assimilation. That was one group of papers at the top row here. The second group of paper did they learned the overall structure. They told you how to develop an ensemble of computations that best explored phase space. That's a very important area. They learned the effective potential to do coarse graining. And the third class is, which is actually the easiest to understand and possibly the most important, which is very simple. You just replace the simulation or part of the simulation with a deep learning surrogate. And I will largely discuss surrogates now, although the other uses of machine learning are very important as well. So here's work I did with colleagues at Indiana University. And it is a classic, it is actually typical, it's representative of lots of papers where we take a classic HPC simulation, this time here's molecular dynamics, and we replace that molecular dynamics by deep learning network. You can see that at the top right, it has 4 layers, two hidden layers, and it starts with 5 inputs, which define the simulation, and ends up with 150 outputs, which are measured densities. And what's surprising is you only need 5,000 simulations in your training set to get good answers. If you look at the bottom right, you see a comparison. There are 3 straight lines. Well, the fact they're straight lines of slope 1 says that the surrogate, which is this deep learning thing at the top, compared to the testing set, which are the simulations we didn't use to train, they show a pretty flat, pretty clear correspondence. This has lots of interesting applications. This is pretty interesting for education because it means that if you want to do simulations in your classes, you can do those simulations in an incredibly short time compared to actually running them for real. Because the difference in speed between the sequential molecular dynamics and the sequential inference using the deep learning is a factor of 1,000,000 for this particular problem. General Electric, for example, uses this general idea for computational flow dynamics to incorporate interactive engine design for their engineers. They only actually use 200 samples in their training set and get good enough answers to design aircraft engines. So this is pretty promising. The only issue is you need to have enough uses of the simulation that is worth producing this neural net. If you're only doing one cosmic calculation, this will not speed it up. If you're doing many representative computations where you need to explore parameter space, then this has a huge gain. There's been a recent paper here from January which has done it just had several interesting things it's done. It looked at 10 different cases including climate. That was the largest simulations. And it found a speed up that went up to 2 billion, because that's the title of the paper. And they interestingly had a rather more complicated network than we used, which was dynamically chosen effectively by an automatic hyperparameter choice. And they also discussed something which is pretty important, is we need to be able to calculate not only the value but also the error, and they also discussed that, although not in quite such a I don't think they have the final answer there. Now here's a second application which I think is quite promising, which is if you think about this, actually apply. You mentioned I work in epidemiology in your kind introduction. So in epidemiology, you have operators which, given the current date of infection, it predicts the number of deaths and cases in the future. So that's an operator which translates today's values into tomorrow's values. And that's, of course, traditionally what you do with discretized differential equations or systems represented by coupled differential equations, and those operators are normally done by some simple numerical approximation. But we can also use deep learning to do those operators, and that's illustrated here. And here we've taken actually here's 16 particles. We have replaced Newton's laws with a simple numerical approximation by a recurrent neural net using a couple of LSTM layers. And what is striking about this, which I don't think we expected, this is also with Vikram and JCS, my colleagues here, you can learn to do a time step which is 4,000 times longer than the time step used in the traditional, which needs to be used to get reliable answers for molecular dynamics. So I think this is possibly a good example of something you'll see more of. We'll be able to learn using deep learning how to represent sort of fundamental entities and how they evolve in time. The two graphs at the bottom show in the middle it shows the error for molecular dynamics, which as soon as you go past the time step of 0.001, which gives reliable answers, that error drastically increases. Whereas for the recurrent neural net, you can do this time step of 4, which is 4,000 times bigger, and the error is pretty flat up to times of 1 million. And as far as we know, it will continue to be flat. These are shown here with lots of differential, with lots of different, they're not 16 particles, but 1 particle. We have in the top middle the molecular dynamics error, which increases as a function of time for a time step of 0.01, which is 10 times the reliable number. Whereas for these 3 different potentials, Leonard-Jones, simple harmonic oscillator, and double well, you will find flat errors up to, here we've only shown up to 10,000, but it's flat up to 100,000, up to 1 million as well. So this is pretty interesting, it seems to me, and there's another way that we can use machine learning to enhance HPC, and I think that will be quite important. So here's a summary of this discussion of using machine learning. I think it's extremely promising. It's, for instance, used today in, to replace what in chem informatics is called QSAR, to map drug structure to drug properties so that you can much more quickly identify promising drugs. There was the various web announcements which you can find showing this progress. I gave you examples of surrogates for large-scale simulations. One we're working on here is agent-based simulations. That's actually what these epidemiological systems are. You can instead of, you can actually learn the agent, replace the agent by a surrogate, and then every simulation gets a significant performance increase because instead of solving ODEs for the agents, we actually just have a simple deep learning lookup. We're doing that actually for virtual tissues, where the agents are the cells, and the agents are people for epidemiology and cells for virtual tissues. People have shown how to use these ideas to learn potentials. I mentioned the smart ensembles, where some papers have also seen speed ups of 10 to the 8th. This is just similar to those for surrogates. It's also been used for looking at clouds and turbulence, and looking at microscale structure. And then at the end of just the last couple of slides, I showed how to use recurrent neural nets. I think in all of these, maybe one of the major things that needs a lot more research is trying to understand errors as well as values. And I'm pretty certain that we can make progress there. There have been some important work in that area, but it's not been pervasively applied. Here is a little section here, which is related but slightly different. And so I spent some time working with this largely industry organization, which is called MLPerf. This slide here is sort of a collage of different MLPerf images. To the right, you have the 80 companies which are involved. There are also a few universities which are involved. And then they produce things such as the chart at the bottom left, which is their training benchmark, which has lots of different training benchmarks. And then we have this competition largely between Google and NVIDIA as to their performance. And I think this organization is pretty important because it really is giving you very quantitative benchmarks. So I'm proposing to set up a science data working group inside MLPerf. So as well as natural language processing, and we can also do science data benchmarks. As far as I know, there is no scientific data benchmarking activity with the same flavor as MLPerf, and this will not only enable you to understand which like the previous talk did, the performance of different systems on different problems. We can also actually capture, say, the work on surrogates and give some example surrogates with tutorials attached to the benchmarks, which will help other fields develop surrogates for them. So I think as we now are switching from into deep learning approaches, to have benchmarks which capped with tutorials will be pretty helpful. So I've been working with my colleagues Tony Hay and Yehan in the United Kingdom to produce an initial set of science benchmarks. We have, I listed them here. 2 of them are those machine learning for HPC surrogates that I mentioned. The first 3 here are large-scale science image benchmarks or applications, which we believe we can make into benchmarks where each benchmark will have a open source data set, a reference implementation to challenge you, and you'll be encouraged to produce better predictions and better error estimates than we can do. So that just sort of summarizes this part of the talk, that we think we will try to cover a broader range of science areas. We currently are pretty limited, a bit on surrogates and a bit on some environmental science images. And there is already an HPC working group, and we will continue, which I work quite closely with. We'll continue to work with them, also with several of the other MLPerf working groups. All right, so that's just an area which I think is pretty promising. And if anybody has data sets and implementations they'd like to work with us on, please contact me. All right, the last part of this talk is on the data engineering part of things. So if we look at these big data systems, I remember I showed you that previous slide that we wanted to understand how to solve the big data systems and the deep learning, which is a critical, but in terms of lines of code, probably small part of the system. And we know that the typical systems that are used to do this, they're Spark and Flink for batch processing, and Heron or Storm, and related systems for streaming. I guess Spark and Flink also do streaming. And of course, Hadoop was the original major player here. So if you try to see how to add high performance to those big data systems, you want to add the high performance to the overall system and also to that thing in the middle, the deep learning. Now, the thing in the middle is probably going to be done by TensorFlow and PyTorch and associated Jupyter notebooks and things like that. And you probably don't want to, you want to keep that to run as well as it possibly can, as we heard again in that talk before me, and just provide a broader high performance environment. So that's the last few slides are on that goal. So if you look at everything you need to do this, is quite a lot. And this slide here summarizes the components you need to do. You have to you have some systems about how you support parallel computing. When millions of years ago, I worked on things like the owner computes rule and things like that. We need to, of course, do we need to map resources to what's called maps in MapReduce and things like that. And we have to, of course, today worry about containers. And we have to cope with the issues about Slurm and related systems, because Slurm is dominant in HPC and probably Yarn Yarn or Kubernetes are dominant in the big data system. So we need to worry about that. There's lots of components connected with tasks, and the second set of capabilities are Sorry, I had an interrupt. That's one trouble about talking from home. You get interrupted. I apologize.
No worries.
I was worried that happens because that keeps happening here. Okay, so here we have the second slide. About the components. So these are just the areas you need to address to build a big data engineering system, and they are addressed in Hadoop and Spark and Flink and Storm and Heron and things like that. And you can see we have to do the data management, the deep learning, the fault tolerance, communication systems, and things like that. So we have a system we call Twister2 that tries to address this, and it, compared to say Spark or Flink, it tries to build in high performance computing in all parts of the problem. It runs either Kubernetes or Slurm, because there's some things where if you're really dominated by MPI, still Slurm does a better job than Kubernetes. We used to have Mesos on this slide, but Mesos seems to be no longer used as much. One aspect of these systems which is important is we need to be careful in thinking about how to do communication. Namely, there are different communication requirements that need different systems. Namely, we need to do data flow and data flow communication, which is actually what's supported by, say, Spark and Flink. That has different requirements from, say, the one that MPI addresses, because typically for MPI, when you do communication, you're moving data from a set of tasks to the same set of tasks. In data flow, you communicate from one set of tasks to a separate set of tasks. Then you have a third type of communication, which you need to do for streaming, where you get streaming events or communicating events from the edge to the cloud. And there are all sorts of things such as RDDs, and they're called streamlets in Storm and Heron, and data sets in Flink, and P collections in Apache Beam. So Twister2 is just listed here in its raw characteristics. Most of my students actually come from Sri Lanka, and that's where most of the developers are. I also have students in Turkey. Previously, I just tried to modify Hadoop and Spark and Heron, but we found that we reached diminishing returns, and this has around 120,000 lines of new code. So here are a few slides on performance. Originally, this is an old slide because it just pointed out, and actually possibly not so relevant, because this is classic machine learning, multidimensional scaling, which happens to have multiple parallel sections, which Spark and Flink do very poorly on, whereas a natural MPI system, which will be supported by Twister2, runs quite well with, and there's factors of 100 to 1,000 difference. That's because here with the multiple parallel sections, the Spark and Flink do not do well on the owner compute stream. Here we have this slide about the data flow. We built a data flow library, whereas MPI is a good library for moving from processes to the same processes. If we want to go to different processes and do data flow, then you need a different library, which you can use the same software, but needs to be packaged differently. And this picture on the bottom right shows the difference between the bulk synchronous processing style from process to the same process and the data flow style to different processes. I should point out we have both a Java and a C++ implementation of this. And of course, here are some sorting results. So, because these systems don't do classic machine learning and things like TerraSort, this shows that Twister2 outperforms, in this case, Spark, but if we did Flink, it would outperform Flink. Just because it's built into its data flow library is much faster than their data flow library. Here's a typical machine learning, a support vector machine showing better performance for the Twister 2. And Twister 2 has various ways of running depending on the level of the interaction, and they have roughly the same performance, with the MPI version being somewhat faster than the with the different levels of high-level interaction which Twister 2 has. Here is Twister 2 running on streaming SVM application, and again, it clearly outperforms, in this case, Storm and Flink. I'm nearly finished.
Lower is better.
Sorry?
That we noticed in this data is that the first.
Sorry, is there a problem?
Can we save the questions for the end, please? Yeah, go ahead, Geoffrey.
All right, so I just wanted here's this sort of plot of I wanted to come back to this picture here, which shows the deep learning red curve, red blob in the middle of everything else. And we try to show this in a different fashion in this slide here, where in the middle we have the training and inference. That's the deep learning, which is presumably, at least if it's down at Indiana, we done using Jupyter Notebooks or Google Colab. And then around this, we have all this data engineering with pre-processing and post-processing. And we're trying to see how to make these data engineering interact well with the Python and GPU-based systems in the middle. And so we added this thing, Twister X, or Twister 2, which is the C++ kernel. We have to do C++ because we don't know how to interact with high performance with Python from Java. And we use these Apache Parquet, which is a high-performance storage system, and Apache Arrow, which is a high-performance in memory multi-language system. And we introduce a table API, which allows us to interface with pandas and other Python, NumPy, and things like that. So we just sort of finished the first version of that, which is then meant to be an interface from this broad data engineering, which was the first part of this discussion, to the high-performance deep learning subsystem. And by the way, I don't see a lot of discussion of how you're meant to do this in the literature. And in fact, if you again, I come back to this MLSys conference, none of the papers discuss this issue of how we relate these two parts of the system. And here's the C++. Here's yet another comparison, this time a join operation, showing that actually here Spark and Twister 2 have about the same performance, and the C++ version where you have Twister X outperforms both of that. And here on Python, then we can compare Twister X with Spark interfacing with Python, and we have much higher performance because of our use of Arrow. And here's the final slide. And I discussed several things here. I had a little section on benchmarks where I think would be quite important for science if we can take some of these early developed applications in data analytics, like say in the first talk, and capture them as a benchmark, which will then teach other people how to develop such examples, as well as giving challenges to the vendors to get better hardware and software. I then pointed out how this is what I call ML for HPC, using machine learning to enhance HPC is very promising. And in general, I see the field is pretty confused because we switched from machine learning to deep learning, and the implications of that are not properly understood, in my opinion. Maybe I'm wrong. And I then introduced Twister X and Twister 2, which try to do both data engineering and interface to deep learning. And this doesn't have the full features of Spark, but it has many of them. And it does have attention to HPC in both the in all aspects of the needed system. So I don't think I don't have any complete solutions here, but I've tried to address some issues which don't seem to be clearly addressed elsewhere. And I see the whole field as really promising, because we can, as we heard in that first talk, deep learning is enabling us to do many things that we have not been able to do in the past, and so we need to learn how to do that. So that's the, and I think HPC is really important in doing that, even if it doesn't seem to get so much respect in the academic community. Thank you very much.
All right, thank you. Are there any questions for Professor Fox? I think someone had a comment or a question in the middle of the talk. You can ask it now. Yeah, so I have a question. So you talked early on about using these DL models as surrogates for some simulations. It's a very interesting use that I wasn't familiar with. This is very different from the usual DL models that you train to do like image classification or things like that. Are there unique infrastructure challenges trying to train and serve these surrogate models?
Well, I would say that's not terribly well understood, because this paper I mentioned, which has this provocative title with a 2 billion speed up in the title of the paper, it was the first actually which tried to really look in detail at the correct appropriate architecture for the deep learning network. And theirs was pretty complicated, whereas the earlier papers, like the one we had much simpler networks. And I think a critical issue is learning the errors, because if we're going to be really using these on a daily basis, like say General Electric is using this idea of surrogates to do real-time aircraft engine design, well, we better have some confidence that the answer is right, and if we really think we've captured all of phase space, and we know these are physical systems with very complicated phase spaces, and to know that we explored the phase space in the training set correctly is, I think, pretty challenging. So I think that's an area of huge importance.
Yeah, and this point about modeling the errors, is that do you think that'll require more fundamental changes to neural net architectures, or how you do SGD and things like that?
Well, I mean, there's some early papers using Bayesian learning which has actual distributions to tie to the learned parameters, but that doesn't seem to be practical in general. So the work I'm familiar with uses dropout to estimate the error. They either use dropout or just effectively variation in hyperparameters to estimate the error. But I don't think that's very systematic, and nor does it really address. I mean, my Ph.D. is in physics, so I like physics phase spaces, and it doesn't really address the fact, have you actually explored the phase space, which is something which is called ergodic in physics. Namely, how do we really make certain that you can reliably use these networks when you plug in the value and you get an answer? Well, maybe that answer is completely wrong, because that particular set of parameters is in a region of phase space which is in a different phase, or all sorts of things could happen. I think much more work is needed in that.
Okay. Interesting points. Any other questions for Professor Fox?
Yes. So Vinod, I have one question. This is to Professor Fox. Hi. Hello, Professor Fox. So I have one question that with a lot of work going around automating the end-to-end pipeline for machine learning in like for NLP and vision, to make it easy and accessible for data scientists to use the entire machine learning pipeline and get away with the complexities of that you were pointing out of the data engineering surrounding the model and that work from the hidden cost. Do you see efforts going around in developing these machine learning pipelines and automating them like using Kubeflow or certain technologies for the HPC community or HPC models?
Well, as I mentioned, I'm actually surprised that this topic is not very well discussed. I don't see many papers, because if you look at let's go 5 years ago, then we were doing, when we didn't really have so much attention to deep learning, and then things like Spark and Flink with, there were things like MLlib from Spark, but I don't think that's the right approach these days, and I don't think there's much attention to it. Spark is still a dominant effect, but you sort of think of now of the world as Spark plus deep learning. And the interface, whereas previously actually we thought of machine learning as integrated into the Spark or Hadoop or Flink. But I don't think that's true any longer. That's what I tried to discuss, that even in our system, Twister2, to actually interface Twister2 to the deep learning was not trivial, because the deep learning tended to have a Python front end, and that didn't interact very well with Java. Java is pretty inefficient interacting with Python. And I'm not quite certain actually how. Well, we heard a talk from IBM second. How the major how the companies actually address this in practice. It's not. I don't see a lot of papers from the academic community.
Okay, thank you.
Yeah, it certainly motivates another area of research. Yep, and thanks, Professor Fox, again. I think in the interest of time, we need to move on to the next talk. Thank you.